Let's talk about some of the energy relationships for simple harmonic motion. This turns out to be easiest if you look at a frictionless surface on which there's a mass of mass m, a spring attached to it with spring constant k, and it's oscillating back and forth from positive a to negative a and goes through the equilibrium point 0. Now, as it turns out, this is exactly the same as a vertical spring. I'm going to pull it down to a right here, and it oscillates back and forth from A to through 0 to negative A. In this situation, vertically, you might think it's more complicated because gravity's acting too, but because gravity is a constant force, all that does is it lowers the equilibrium point. So our net force is just the force of the spring, as long as you count that 0 point right there as the equilibrium point. If it wasn't for gravity, the equilibrium point would be up higher. So that brings us to back to this situation, which is identical. And we're going to look at a couple different positions on this cycle to analyze the energy. So we're going to start the simple harmonic motion by stretching the spring to x equals a. So it's going to be stretched out to x equals a, the maximum displacement. And you might guess, well, if it's at a and its velocity is 0, what's its energy? What form is the energy all in if velocity is 0? Our spring has been stretched. It is all spring potential energy. So because spring potential energy is 1/2 kx squared, when it's at x equals a, the energy, the spring potential energy, is just 1/2 k a squared. And because energy is conserved in this situation, this is going to be the energy at all times. That will be the total energy. It's always got to equal this because we're not going to add or take away any energy. We're on a frictionless surface right here. It won't be any work non-conservative. The spring work that does, we're just going to keep track of that using spring potential energy. No work non-conservative. This will be the total energy at all times. So let's express that total energy a couple different ways. At time equals, so this was at time equals 0, at 1/4 of the period, 1/4 of the way through the cycle, it has moved to right here. Now, what is the potential energy when it's at x equals 0? The string is neither stretched nor compressed. What's the potential energy? 0. So it all must be in the form of kinetic energy. The total energy here is 1/2 mv squared, where v is v max, and it's going in the negative direction. We've defined that way as positive, to the right as positive. So this is a negative velocity. All the energy is in the form of kinetic. And what will be the relationship of the energy 1/2 mv max squared compared to this? Ask yourself that. How will the kinetic energy it has right here compared to the potential energy, the spring potential energy it had right there? If you say they'll be equal, you're right, because we haven't lost any energy. So let's keep going down here and take a look at the next situation. At t equals halfway through the cycle, the time equals the period over 2. Now it's at the other extreme. It's at negative a. V is again 0. What is the energy here? Well, it's again all spring potential energy. So all the energy is in the form of spring potential energy 1/2 k a squared again, or even if you have negative a, that's the same as, when you square that, that's the same as a squared. And as you can imagine, at 3/4 of the way through the cycle, it's back at the equilibrium point, moving with V max in a positive direction. And again, all the energy is in form of kinetic. Now, how about at an arbitrary position, some arbitrary position x? So any position x, so it's not at the extreme, it's not at A, and it's not the equilibrium point. How can we express the energy? Well, because at any arbitrary position, its energy is going to consist of kinetic, 1/2 mv squared, plus potential, 1/2 kx squared. Notice we're not using A here because it's not at the extreme. It'll be the kinetic energy plus the potential spring energy. That is at any arbitrary point. Now, because the total energy, it always has to be 1 half Ka squared, because back up here, back right there, you can see this is the expression for the total energy right here. That is the total energy is never going to change, and we've found an expression right there for the total energy that the sum of the energies always has to be equal to that. So we can express this important relationship like this. 1 half mv squared, this is at any arbitrary time, the kinetic energy, which is right here, there's the kinetic energy term, plus the potential energy, which is right here, that has to equal our constant of total energy, which will be right here. Those three have to, this plus this always has to equal that. So if you know the amplitude of the motion, you can write this equation and you can solve for v in terms of k, m, x, and a. So I'm going to leave that for you to do so you can get an expression for v in terms of the k of the spring, the mass of the object, the displacement at any time, and the maximum displacement A. Now, let me ask you this. What would you do if you don't know what the amplitude is, but you do know V max? How could you make a similar relationship if you don't know the amplitude, but you know what the maximum speed is? One example of that is if we started at the equilibrium point, if we started with the object right there and we just shot it to the right with some initial speed v. What kind of relationship could you write then? Think about that. Well, as you might guess, we can't express the total energy in terms of A anymore if we don't know A. How could we express the total energy if we know V max? You might guess that we do this. 1 half mv squared, same as before, plus 1 half kx squared, same as before, but now we can express that as equaling 1 half mv max squared. So even if we don't know A, we can write this relationship. Using energy relationships is a really good way to solve for a lot of these things, because energy, as always, is one of the simplest ways to deal with motion.